Hi, this is John Whitaker for the Probability 1 class, and this is our 27th, I think, video lecture. And today we want to talk about compound random variables and give an identity for it. And let's start off by recalling what a compound random variable is. So, as a definition, if we let x of 1, x of 2, and so forth be a sequence of identically distributed and independent random variables let n be a non-negative integer value random variable that is independent of the sequence of random variables x of 1, x of 2, forever. Then S of big N equal to the sum as I runs from 1 to big N of x of I is said to be a compound random variable, and we can define, okay, and we do define S of 0 to be equal to 0, so we can talk about that. Now, that's something we had talked about before, and as a new definition, in a compound random variable, the distribution of n is called the compounding distribution. Okay? It's called the compounding distribution. Okay, so here's a proposition and this is called the compound random variable identity. Okay. So here we let M be a random variable that is independent of the sequence of random variables x sub 1, x sub 2, and so forth, and satisfying that the probability that m is equal to little n is equal to n times the probability that big N for the compound random variable is equal to little n over the expected value of big N, where n is equal to 1, 2, forever. Okay. Then for any function h the expected value of s sub n times h evaluated at s sub n, okay, the expected value of that will be equal to the expected value of n times the expected value of x sub 1 times h sub m Okay, let's look at the proof of this. Okay, so we'll start off with what we want to deal with. That's the expected value of s sub n times h of s sub n. And let us replace what s sub n is equal to. So this is the same thing as the expected value of the sum as I runs from 1 to big N of x sub I, and then times h of s sub n. Okay, and now we will compute this by conditioning on n. So this is equal to the sum as n runs from 0 to infinity, by a fact we've given before, the expected value of this quantity here given n equals to n times the probability that big N equals to n. Again, this is by conditioning on big N. That's what we're doing. All right, and that is equal to the sum as n runs from 0 to infinity of the expected value. Here I made a mistake. This is I runs from 1 and it was to big N. Okay? Here we have the expected value of the sum. Well, if we know big N is equal, if we're given that, then I can replace the big N's by n. So this is I running from 1 to little n of x sub I, h of s sub little n, given n equals to big N, times the probability that n equals to big N. Now we have independence here between n and the x sub i's, and the h of the sum of the n's would s sub little n. And so due to independence, we can rewrite that sum we have the following way. This is equal to the sum as n runs from 0 to infinity of the expected value of the sum as I runs from 1 to little n of x sub I times h of s sub n, just that, times the probability that big N equals to n. Okay? Again, this is due to independence between of n with the sequence x sub 1, x sub 2, whatever. Well, an expected value of a sum is the sum of expected values. So this n runs from 0 to infinity. The sum as I runs from 1 to little n of the expected value of x sub I, h of s sub n, times the probability that n is equal to little n. All right. Here, let me make a comment. We can rewrite this due to, because the x sub 1, x sub 2, and so forth are independent and identically distributed, and the symmetry, I'll say, of h of s sub n, then, let's squeeze this in here, the expected value of x sub I times h of s sub n is equal to the expected value of x sub 1 times h of s sub n. Okay? And this is for all I element of 1, 2, forever, or up to n, I should say. That's what we're doing. I'd like to explain that a little further. This can be seen for example, okay, by comparing the expected value of x sub 1 times h of s sub n and the expected value of x sub 2 times h of s sub n, where the x of 1, x of 2s, I'm going to say, are all discrete random variables. Okay, so here, if we know the expected value of x of 1, h of s of n, okay, that's equal to, well, it's a sum over x of 1 values, sum over x of 2 values, all the way up to sum over x of n values, that's how many I have, of x of 1 times h of x of 1 plus x of 2, all the way up to plus x of n. And then we multiply that by the joint PMF, x of 1, x of 2, all the way up to x of n. Okay? And now these are independent. So this is equal to sum over x of 1, x of 2, all the way over all the x of n's of x of 1, h of x of 1 plus x of 2 plus x of n. And here this is f of x of 1, f of x of 2, all the way up to f of x of n. Now, this I'm going to tell you is the same thing as, I could rewrite this as the sum over the x of 2 sum over the x of 1s. What am I doing here? I'm just replacing x of 1 by x of 2 and x of 2 by x of 1 because they're identically distributed. Sum over the x of n's. And here I'm going to write down x of 2. And then h of, I'll write this down as x of 1 plus, I'll write this down as x of 2 plus x of 1. And these are exactly the same quantities. Because if you write down h of x of 1 plus x of 2 all the way to x of n, you could switch any two of them and you still get the same thing. Okay? And then here, this will be f of x of 2, f of x of 1, f of x of n. And that can be rewritten. As the expected value of x of 2 times h of s of n. Okay. So, the expected value, where we were, of s of n, h of s of n, what we're interested in, that's equal to the sum as n runs from 0 to infinity. We had a double sum here, but we can replace that inner sum by n times the expected value of x of 1 times h of s of n times the probability that big N is equal to little n. Now, rewriting this in terms of the random variable m, okay, this would be equal to the expected value of big N. What I'm going to do is replace n times the probability that n is equal to n by the probability of m equal to little n. So this expected value of n, which doesn't depend on this indices number. Here, this is going to be equal to the sum of the expected value, as n runs from 0 to infinity, of the expected value of x of 1, h of s of n, times the probability that m is equal to n. That's equal to the expected value of n times the sum as n runs from 0 to infinity of the expected value of x sub 1, h evaluated s of n, given m equals to n times the probability that m is equal to n. And we're going in this direction due to the independence m is from the x's, the x of i's. So we had gone in this direction earlier in the proof. Now we're going in this direction. So this is equal to the expected value of n. Here, this is the sum as n runs from 0 to infinity. Now we know that big M is equal to little n, so going backwards, this is the expected value of x sub 1 of h of s of big M, given M equals to n, times the probability that M equals to n. And that's equal to the expected value n times the expected value of x sub 1 times h of s sub m. And that concludes what we wanted to say about this theorem. That's the proof. Wonderful. Now what we're going to do next is look at a corollary for this. And the corollary is something we're going to use. It says let S of n be a compound random variable and suppose that x sub 1, x sub 2 are positive integer value random variables. And for notation, let alpha sub j equal to the probability that x sub 1 equals to j, where j is greater than 0. And, this is not notation, m is a random variable that is independent of the sequence of x sub 1, x sub 2, and so forth. Then, E of S of n equals to 0 is equal to the probability that S of n equals 0 is the probability that n equals to 0. And, oh gosh, I forgot something. Sorry. So, I need to say something more about the probability of, I need to say something more about m. So m is this random variable, it's independent of the sequence of the x of 1, x of 2, and the probability of m equaling to little n is n times the probability of big N equals to little n over the expected value of n. Then, the probability that S sub n equals to 0 is equal to the probability that n equals to 0, and the more telling statement is that S of n, the probability that S of n is equal to k, bigger than 0 energy, is equal to k, 1 over k, times the expected value of n, times the sum as j runs from 1 to k of j times alpha sub j times the probability that S of m minus 1 equals to k minus j. So that's what we want to prove. This part's easy. Okay, here's proof. For k being fixed, okay, now this statement was true here for k being greater than, we're done with this. What we're thinking is k is greater than j. I'm sorry, greater than 0. K is equal to 0, here it is. For k being fixed, we let h of x be equal to 1 if x equals to k, and we let it be 0 if x is different from k. So we're finding this function. Okay, so what do we notice about this? We note that S of n of S of n times h of S of n, okay, it's going to be equal to k if S of n equals to k, and it's going to be 0 otherwise. So that's what that quantity is. Okay, therefore, the expected value of S sub n, of h of S sub n, is going to be equal to k times the probability that S sub n equals to k. So we can think of this as in some sense, a discrete random variable, and here's the answer for its expected value. Now, by the compound identity, compound variable identity, we have this quantity, which I'll rewrite as k times the probability that S of n is equal to k. Well, that's going to be equal to, by the compound variable identity, it's going to be equal to the expected value of n times the expected value of x of 1 times h of S of m. Okay. Which equals the expected value of n times the sum as j runs from 1 to infinity of the expected value of x of 1 times h of s of m, given, let's work with x of 1 equal to j times the probability that x of 1 equals to j. So we're conditioning on x of 1. And that's equal to the expected value of n times the sum as j runs from 1 to infinity of, just symbolically, this is the conditional expectation of x of 1, h of s of m, given x of 1 equals to j, times, as I said, just symbolically, we write down the probability that x of 1 equals to j as a sub j. Symbolically add. Okay? And that's equal to the expected value of n times the sum as j runs from 1 to infinity, and here we know x of 1 is equal to j, so this is the expected value of j times h of s of m, given x of 1 equals to j, times alpha sub j. The expected value of a constant times something, you can pull out the constant, so this is expected value again, sum j runs from 1 to infinity of j times the expected value of h of s sub m, given x of 1 equals to j times alpha sub j. Now I'm doing that here using properties of conditional expectations. That's equal to the expected value of n times the sum as j runs from 1 to infinity of j, and now here computing this this conditional expectation, this is the sum, as I'll write down as little s sub m primes, they travel over whatever alpha phase we have, of h of s of m primes, that's the way I'm going to write it, of f of s of m given x of 1, s of m prime, that's the alpha phase, little j, alpha sub j. Now, I'm thinking of that sum, the s of m, big S of m, I'm thinking of it as one random variable, as opposed to breaking it up into multiple random variables. And having multiple summations involved there, more than what I have. So I'm looking at it in this overview type style. This is equal to the expected value of the sum, the expected value in terms of the sum as j runs from 1 to infinity. Okay, this would be j times f of s of m given x of 1 of k given j times alpha sub j, as we have to remember what h of s of m prime is going to be defined by. it's equal to 0, except when S of m prime is equal to k. That's what we have. It's by the definition of this H. Okay, that's equal to expected value of n times the sum as j runs from 1 to infinity of j, and this is the probability that S of m, this will be m here, equals to k, given x of 1 equals to j, times alpha sub j. Okay. Now we want to compute this probability, this conditional probability. We'll concentrate on it. The probability that S sub big M equals to k, given x of 1 equals to j, is the probability of the sum as I runs from 1 to big M of x sub I equals to k, given that x sub 1 equals to j. So all I did here was replace what S of m is given by this sum. That's equal to the probability of j plus the sum as I runs from 2 to m of x sub I is equal to k. So we know x sub 1 is j. We're given that. And so we put ourselves in that position. This is the probability we're being asked. That's equal to the probability that j plus the sum, I'll say, is L runs from 1 to m minus 1 of x sub L equals to k. And this is due to the independence of the sequence in identical distribution of each of the x sub I, and the independence of m from the x sub i's, the sequence of x sub i's. And that's equal to the probability that the sum as L runs from 1 to m minus 1 of x sub L is equal to k minus j. So, k times the probability that S of n equals to k, is what we were working with. That's equal to the expected value of n, so here's where we are, times the sum as j runs from 1 to infinity of j times the probability that S sub m, big M, is equal to k, given x sub 1 equals to j times alpha sub j, that's where we were at some point, is equal to, replace this, we have the expected value of n, we replace this conditional probability with what we found, so it's the sum as j runs from 1 to infinity of j times the probability that S of m minus 1 is equal to k minus j times alpha sub j. So this gives us well, for a second, let me stop. So we think of k as being some positive integer, okay? And here, when j gets bigger than k, the S of m minus 1 can't be equal to something negative. And so we can only go up to when j is less than or equal to k. So I'll write this down in the following way. Now when j is bigger than k, the probability of S of m minus 1 equaling to k minus j equals to 0. So here's what we get. So, k times the probability of S of n equals to k is equal to expected value of n times the sum as j runs from 1 to k of j times alpha sub j, probability that S of m minus 1 is equal to k minus j. That's what we have. Alpha sub j is written there. Wait just a second on me. All right. That's correct. So what we have is the probability that S sub n equals to k is equal to 1 over k, expected value of n, times the sum as j runs from 1 to k of j times alpha sub j times the probability of S of m minus 1 equals to k minus j. Okay, so all I did was divide everything by k. Now, by definition, okay, for n being bigger than or equal to 1, I'm sorry. This statement that I have here is for n being greater than or equal to 1. Okay? That's what we have. Now, by definition, here's what we have. The probability that S of n equals to 0. Okay? That's equal to the probability of the sum as I runs from 0 to n of x of I equals to 0. And that equals to 0. Note, S of 0 is equal to 0. So, the probability that S of n equals to 0 is equal to the probability that big N is equal to 0. And that ends the proof. I'd like to give myself 1 second, please, to look over what's written there. Give you a second. Okay, and then we're going to do a fact, and that'll be it for today. It's just 1 second. Make sure everything's okay. Okay, this should be 1. This statement right here was true for when k was bigger than 0, okay? That's what we have. We have the result we want for when k is bigger than 0. What we're doing here is now looking for the case where k is equal to 0. So here, this is for n being bigger than or equal to 1. That's what my notes said. I got a little confused, okay? So here, this statement, we got the result we wanted for when k is bigger than 0. Now here, if we look at the probability for all n being greater than or equal to 1, S of n equal to 0. That's the probability that as I runs from 1 to summation of n of x sub I, that's equal to 0. And the reason that's equal to 0 is we're assuming here that the xi's are non-negative. Okay? Or not only non-negative, but positive integers. And so they're going to be something bigger than 0. So that's 0. But S of 0 was defined to be 0. Okay? So the only time that S of n is equal to 0 is when n is equal to 0. And so that's the probability is n equal to 0. Thank you very much. Let me explain that. Okay, here is the last thing I wanted to write up. It's a fact, I'm going to prove it. And it says, let n be a Poisson random variable with mean lambda. Let m be a random variable such that the probability that m equals to n is equal to n times the probability that big N equals to n over the expected value of n. And here n is equal to 1, 2, 3, forever. Okay. Then m minus 1 is Poisson with mean lambda. Proof. So note the probability that m minus 1 is equal to little n by what's written right here. Well, first of all, this is the same thing as the probability that m is equal to n plus 1. And so by what's written here, this is equal to n plus 1 times the probability that big N is equal to n plus 1 all over the expected value of n. All right. Now, that's equal to n plus 1. Now, the probability that n is equal to little n plus 1, since we know that n is Poisson, that's equal to e to the minus lambda, lambda to the n plus 1, all over, it's n plus 1 factorial, and then all that is over the expected value of n, which is lambda. So this lambda will be put here at the bottom. This n plus 1 will cancel out with 1, the n plus 1 there. We'll get e to the minus lambda. It's e to the minus lambda. Lambda to the n plus 1 over lambda times n factorial. One of the lambdas in n plus 1 with this lambda cancel. We're left with e to the minus lambda, lambda to the n over n factorial. So that tells me the n minus 1, its probability mass function is that of a Poisson random variable. Is Poisson with mean lambda. That ends this video. Ladies and gentlemen, that is enough for video 27. We'll start with an example of the corollary that we had with the Poisson random variable being involved
next time. Thank you very much.